Well, good evening. I just wanted to do a short video. Given my channel's history so far, that could be anywhere from 10 minutes to 1 hour. But I wanted to do a short video on the 778D Dual Directional Coupler. I wanted to buy a directional coupler for my bench here, my workshop, and these were being auctioned off on one of the auction sites. And as things go, I ended up winning both lots of 3 of these things. And it turns out that I got 3 of the 3, so I have 6 of them now. I got 3 that work properly and 3 that don't. And by work properly, what I mean is 3 that will pass the key site calibration testing and 3 that just fail, and they fail in a specific test on the return loss, on the test port directivity, sorry. Anyway, the reason I wanted one of these things is because they're very handy tools to have in your lab. You can use these couplers to do things like measuring return loss, measuring insertion loss. You can look at power monitoring, you can do signal combinations and so on. One of the common things that's done is that return loss measurement. And typically you might have seen return loss being done with a unit like this. Let me zoom this in. This is a little cheap SWR bridge. It goes from 1 megahertz to 1 gigahertz. And really an SWR bridge, and I won't go into SWR return loss and so on. It seems to be one of those things. I'm a digital guy, so I'm not really a historical expert in a lot of this, but from my reading, it appears that a bunch of the radio guys, just in the high frequency and so on era, referred to things as standing wave ratio, or SWR, VSWR, voltage standing wave ratio. Whereas a lot of the microwave and later engineers talk in terms of return loss. And return loss has a unit of dB, and VSWR, SWR is just simply a ratio, 1 to 1.05 or 1.1 to 1.13, that sort of thing. Anyway, what it does is basically gives you an idea of how effective the device under test, the DUT here, how effective that is at consuming the power or taking the power from the line. If you had an infinite return loss or a 1-to-1 SWR, basically all of the RF input that you'd be putting in here would be disappearing into the device under test, and there would be nothing reflected back out. And so this is what is going on in the coupler. Is basically the coupler is taking the reflected signal, and so it's able to say, I'm going to ignore the inputted signal, and I'm only going to look to see what's reflected off the end here. And so that coupling is, these are passive devices. That coupling is actually, sort of non-directional, right? So what I could do is I could flip that around, and I could put my power in here, have my device out on one side. Now I'm sort of getting confused, but I can put the power in, have my device on one end, and then monitor what the incident power is. If you combine 2 of these together, what you get is this guy here. You get the, let me just zoom that out, you get the dual directional coupler. And so if we look at it, the input's up here, and I feed in the RF power, I feed in the signal, it goes to the test port. So I connect my source to here and my test device to here. If there is a reflected signal, which is the same as this guy here, that comes back and then gets measured or presented on this port here. Now there's also an incident coupling as well. I talked about how you could turn that around and use it in the other direction. Well, that's what's going on here. So these dual directional couplers are great, because what I can do is I can measure the amount of incident coupling here, and that then lets me know what signal level that I'm putting into the device. If I know that this is going to be very accurately at, say, 20 dB, then if I put a signal in here and I'm measuring it here, if I put 0 dBm into it, I should be measuring minus 20. And so it gives me a way of seeing the exact signal level that's going into my device. Now, typically, you'll get 20 or so dB loss here, and you'll get half a dB in insertion over the entire device. And then the reflected thing does the same bit here. Whatever the reflected value is, you get like 20 dB less coming out here. Then there's also a bunch of what they call directivity, which is, how much of the signal that goes in here appears here just because of the device. How much of the signal goes in here appears here just because of the device. And so the reflected test coupling part was what this particular device and the other two that are like it was failing. So I thought, well, let's take it apart and have a look at what is inside. So to do that, I'm going to grab my 9/64ths, because these are of that era, and then I'm just going to go and undo these. So bear with me while I undo it. We'll speed this up so you won't have to listen to the whole thing. Okay, so let's just turn that over. Did all of those screws come out? Yes, they did. Okay, let's just put all those screws up here. Okay, so now what I'm going to go do is I'm going to go take the top off, and you'll see that this is this beautiful RF construction. It's all machined aluminium. And on top of here, let's see if I can zoom in now. This thing doesn't zoom in real well on, well, there you go. It generally doesn't zoom in really well on reflective surfaces. But here at the center of this, you can see that there's a milled section and then a little button. There's a milled section and a little button here, and this little button provides, the press against these little circles. So let's zoom back out and let's take these circles out and take a look at the general construction, right? Beautiful layout. Now, I'm not, again, as I said, I'm not an RF guy, and so I asked on the forums, for some information about whether or not, what were they trying to do with these little slugs. Now, the first thought that I had with these little slugs is that they're actually a slightly different material, and so they're doing some sort of tuning of the magnetic field, and they're using that to help ensure a consistent alignment or a consistent field effect down the entire device. That may be true. The alternative is that they may not have anything to do with that at all, and what they may in fact just be doing is simply providing pressure to keep the unit properly straight and properly compressed. Now if we pull up this little metal sheet here, and I'm just going to flip that over here, what you'll see under here is this plastic dielectric insert, and this is, or polymer dielectric. This is going to give a guaranteed dielectric effect, and what they're trying to, I think what they're trying to achieve with this, excuse me, I think what they're trying to achieve with this is to ensure that when this thing is swept, because this operates best from 100 megahertz to 2 gigahertz, that typically when they build these things, that they first started, they worked on the theory that they needed to define the distance and the size of these things so that they would work without generating multiple wavelengths and having multiple nodes and things that appear in there. And I think this is doing something to change again the dielectric effect to help that system become flat across that length. So let me just reach in there and just gently pull this out, and so we can just slide this out, and you'll see that the whole thing pops out. And if you look at it, you may not be able to see it here, but you might just be able to get the little indentations that are on it from the from those little discs. So I sort of lean a little bit myself towards the theory that it's there, those discs are there to keep the system, to keep pressure on it, keep it all straight, and basically keep the dielectric effect to be constant, because as you change humidity and so on, you'll change that effect there. Anyway, let's zoom in a little bit, and what we'll do is we'll go up to the end here, and here you can see how the basic unit works. You have your coupler here connected, and it's soldered into a little plug basically that connects to just a copper trace on more of this material. I believe this is called regolite. I'd have to take a quick look at that. Or it might just be reglite. Anyway, just a copper trace that's been put onto there, and then they've soldered in some little connectors. Now, if you look in here, what you'll see here is actually a bunch of different film of a different lengths all sitting in here, and it's all different lengths on the edge there. So I don't know if you can see that. Maybe if I put the you might be able, yeah, you can see that it's cut at all different lengths. It's a very thin, flat plastic. Again, I think they're playing a bit with the dielectric effect, but as you start to get towards, because if we zoom back out a little bit, how they're achieving the coupling here, and let me move that out of the road. Let's just see if I can get in. How they're achieving the coupling here is just simply by the distance between the trace. So you'll see that at one end the trace is going to be very close. Let me zoom back out a little bit more. At one end you're going to see the trace is going to be very, very close here, and then at the other end it's going to be much further away. And so they take advantage of this to create that directivity, so that this is the incident wave. So the waves that are coming in here are going to be much more tightly coupled to this guy because of the distance of the track, and then as they get further away, they're going to be less, the reflections are going to be less tightly coupled. And then similarly, when you reflect, these are going to be more tightly coupled here, and they're going to be less tightly. Now, these two little things here are a 50 ohm Terminators basically. Fundamentally, that's basically the same as these guys here. What you'll actually have is most of these devices are actually 4-port devices. So they've got the 4 ports and then the 2 terminators in there. Only that one of the ports in this particular case will already have a high precision load put on it, so that you actually only need to connect one port up. But that's that part there. Let's go the next step now and zoom back out a little bit more. Let's take off one of these little terminators, and we will see what's inside there, and you can get a better view of the construction. Now, again, as always, a lot of this gear, HP gear of this era, uses these posi drive screwdrivers. So I have mine, all my posi drives have a little green steer on. So this is the terminated load, and so if we zoom in again, let me just move that out a bit. You can see the load here, and basically, let me see if I took one of these apart to have a look in. This is it here. Basically, if we take this apart, you'll see that there's a little rod, in the middle here, and there's a little ring, clip ring that's in there that holds all that together, and then that basically gives us that's the 50 ohm resistor from here to here, and that's the load which terminates on that end. So let's just screw this all back up together again. These things are fascinating in terms of the construction, and the mathematics and the design and the engineering that would have gone in to working out what the material choice needs to be, what the size of the traces are going to be, trying it out, tuning it in, trying it again. And when you put it into context, and this is one of the things, this is the conceit of the digital engineer, is that this was designed, I think this was actually first disclosed in the HP Journal in 1967. So that's a year before I was born, and it's amazing the amount of development and capability and so on that they could achieve in that era. And that's sort of the conceit, is like, oh my God, look at the design and the math that went behind it, and so on. When people didn't have, like, when slide rules were out there and those guys were top-notch experts in their field. The math hasn't changed, just their tools have changed, and they really did just an incredible job in sort of pioneering this field, and having people learn how this stuff works, and creating all of these basic pieces of kit that have been used from this point on. So what I'm going to do now is I'm just going to try and turn this over. What I might do instead of doing that is just put this back on here, and then this guy sticks in much better. So if we just slide that on and drop that in, and then now what I'm going to go do is just screw in a couple of guys in the middle and a couple in the end, and then we'll put all of the rest of them in. So let's I'm going to go tighten this back up again, and then we'll take a quick look at how it works. Okay, so in the actual construction manual somewhere, there would be a specification that would give you the torque that you're supposed to tighten these down to. What I'm going to do is just simply tighten them up to the point where the little Allen key bent as much as it did when I was undoing them the first time. But there would, HP would absolutely have, like, this is going to be X number of Newton meters or foot pounds or ounce inches or furlong hundredweight or whatever they measured it in then. But this getting these sealed up, these RF devices classically have this multitude of screws that help bind everything together and ensure that there is a sealed container, and that all of this shielding, this case, not only provides reliability and rigidity to ensure that the substrate doesn't move, but it also provides an effective shield that helps protect the signal from outside interference. So this is you know, this is a very common sort of structure. If you've seen even modern spectrum analyzer units and so on, all display similar sort of stuff. So here we are, we're all done now. So I can put that back in my little tool set. Let's zoom right back out. And now we're ready just to throw in a few signals and just to see what happens so that you can see how directional coupler works. So let me set up for that, and then we'll take that shot. Okay, so what I have here is I have my E4418A power meter, and I have this connected to a E9301A power sensor. Now this power sensor can go from -60 to +20 dBm. It's the successor to the 8400 series sensor. Now this is a great little unit because basically all of the calibration factors are stored in the sensor, and then when the sensors are connected, what you get is you get the calibration factors are all uploaded. So they're not like these guys here, where, you know, in the other world, you know, with the 400 series, or the 437B enabled you to actually load these, but the 438 doesn't, and the 436 and 435 clearly don't. And the 8902A enables you to load some as well, but only two things. But these, I could swap these sensors around as much as I like, and those cal factors would be automatically uploaded. So all I need to do is set the frequency, and I already told this that the frequency that we're getting out of this my signal generator, this is coming out of my 8657B, is going to be 1 gigahertz. So we set that up, and it's 1 gigahertz at 0 dBm. So you saw that. Let me actually go back in here. You saw that with the cable, I have a 6-foot RG402 cable, I think this is. You can see it's a little metal braided cable. I have that set up here, and that puts about a dB of signal loss for the 6 feet in. So measuring sort of directly from the my 8657B should be about 0.04 dBm, and with this cable you can see that it's, you know, about -1.3. So what I can do here though is I can actually just zero that out. So let's go in, let's turn rel on, and we'll make this relative. So now we're actually measuring the exact, you know, the power relative to what was coming out. Let's see, make sure I had all that put in there. Coming out of the actual cable. So we don't really need to know exactly what's coming in. So if we go and connect this in here, now the first thing that I'm going to go do is just drop this in here. And I'm only just going to finger tighten these up. You would, if you were making metrology sort of type of measurements, you would actually use, if I can get out, you know, you would use a proper little brake to go and tighten that in until it broke, and then you know that the cable is at, you know, the right, the connector is at the right specified torque. But for the purpose of this, you know, I'm not going to go put it in and then put it on and do all that. So let's just get that in here, and here you can see that you know, I'm reading about 0.3 dB insertion loss. Let me take a quick look at the specs. Alright, so it turns out that HP didn't actually spec an insertion loss as far as I could tell in the manual, but I went and had a look at the CAL documents, and they say a maximum of 1 dB. So as you can see, with a 0.3 dB, this unit's pretty good in terms of the quality of the insertion loss. Now, what's going on here is that signal's flowing down here, but we're actually getting signal out of here as well. So let me move the sensor over, and what you'll be able to see is the signal that is being sent back. Now, this is effectively an open. So this is basically when you look at the, again, I'm not going to go into SWR, but fundamentally this is an infinite load here. So there's a mismatch, so everything is being reflected back. And what you can do is actually go in and you can get these calibration kits. So here I have an economy kit because I'm not really a cal lab and I don't have very expensive gear. But this gives me a proper little open and short here. So I'm just going to connect the open to it. Now, the reason I'm doing that is that there is slight fringing effects that will occur and capacitance and so on. So, you know, what we're sort of seeing here is that at 1 gigahertz, they're so small. You know, we noticed if you looked at it that value is bouncing around from 0.35 to 0.36, and with the proper open on the end, it's pretty solid at 0.35. Because these things are actually related to impedance, not resistance, you know, so there is a combination of like where the wave is and so on. If you put the short on it, you've made this a zero impedance, and so zero impedance load. And so what you're basically going to get is you should still get 100% reflection, but you're going to get it out of phase, and so there will actually be some cancellation of the waves here. And so what we should see is we should see a decrease in the apparent power, because there's going to be a decrease in the coupling effect and so on. At least that's how I understand it, and we can see that right there. Now, if we actually go back in here now and drop in our load, and this is a pretty damn good, accurate load here. This is a HP 909F. If we drop this in here, what we should start to see is, you know, we're seeing 62 and odd dBm of signal now. So we're probably actually at the, and I think this was yeah, see this is, you know, 20 to 60, so this is sort of at the noise floor of this unit. But basically what's going on here is this is incredibly well matched, so there's virtually no signal being reflected. So that's that port, and so it makes sense that you would use this because you want to measure SWR and you want to measure return loss. And so as I was saying, let me go back here and just take that load off again, because there was that difference between SWR and return loss, right? So here we're actually measuring, you know, minus 21.35 dB. Now, Mini Circuits does this nice little converter that will table that will tell you, basically, if you look up what your return loss is, it'll tell you what the SWR of it. So basically what the SWR of this is at minus 21.35, you know, if we go look, it's going to be between, you know, 1.18 and 1.19. You could go and do the math to work it out, but that's basically what we're going to get with that. And if we put this load on it, you know, and that then goes back up to, you know, like over 40, you know, over 60 dB, you know, what that's telling us is that if we look, the top in this table is 46 dB, which is a VSWR of 1.01. So this thing, I think, has a you know, a rated VSWR of 1.0005 or something like that. So I'd expect to see very little deviation there. Now, with that on there, now assuming that, we had some other item that was consuming that, that signal, what I can do is I can actually come in here now, and this is where I could attach my power sensor up here. And at this point, I'm reading, minus 20.92 dBm. And so basically, I know that I could relate that, and in fact just hit rel again and have that set as my 0 dBm. So if I drop my amplitude minus 10 dBm, what I'm now going to be reading is 10 dBm down. So what I can do with this port is actually use this to measure the actual power that I'm putting into the item here. And if I put in a proper little load at the end, you'll see that the signal is slightly different. That's because, again, the standing wave, and I'll link into that great example of what the explanation of what the SWR is. It's fantastic. It's from like the 50s or 60s. It's phenomenal. It really is worth watching. What you're seeing here is now, it's telling me that there's a different amount of power that I'm actually putting in because of this. Now, unfortunately, this unit has some directivity issues, which means that there is going to be reflections coming back, and so this is not going to be quite accurate. And I think 1 gigahertz is actually the problem frequency that this was occurring. But anyway, what you've just seen there is just the fundamental idea of this. So I can put an unknown load of some form in here. I can measure the return loss from the load. I can measure the power. I could then go and put something else behind this. For example, if I wanted to go in and measure, say, a 6 dBm load. Let me see what I've got here. Let me grab a 6 dB attenuator. What I could do is drop the 6 dB attenuator in here. Let's put this back to 0 dBm. Let me take this out of here. Now that I have my attenuator in here, and if I go and connect this up again, I'm having real troubles with these N-type connectors. I'm just not getting the things flat. What we're getting now is we're getting a bit more power bounce back, and so I can now go in and start looking at what is the SWR of the attenuator. I can start getting some information about this, and I can see that there's more signal. If you looked at it, I'm now getting 40 dBm back. So if we looked at the thing, that's the little mini circuit, so that's 1.02 SWR on there. So it gives me a way of measuring getting a bunch of information about all of these different components that can be connected to the directional coupler. Anyway, I hope you found that interesting, and I will catch you again later.